All right, let's just jump right in. We are surrounded by randomness literally every single day. Is it going to rain? Is my team going to win? How many people are going to walk through the door today? It all feels, well, completely unpredictable. But what if I told you there's a way to get a handle on it? A mathematical toolkit, believe it or not, for making sense of it all. And that's exactly what we're going to unpack today. I mean, think about it from a business point of view. Let's say you're running a car dealership. Some days you sell zero, some days one. Maybe on a really great day, you sell five. How on earth do you plan your inventory or your staffing? Especially when the future just feels like a complete roll of the dice. And yeah, while it's totally true you can't know exactly what's going to happen tomorrow, it is absolutely not pure guesswork. There are patterns hidden inside all that randomness, and today we're going to learn exactly how to find them. So that's the big question, isn't it? How do we take this fuzzy, vague idea of uncertainty and actually turn it into real, hard numbers? Numbers we can use to make smarter decisions. That's our whole mission for the next few minutes. And this isn't just some abstract idea. Just look at this real-world example right from the source material, Citibank. They are constantly looking at how many customers show up at their ATMs. They are not guessing. They're using the exact principles we're about to talk about to turn that random flow of people into useful data. Data that helps them manage their services, keep the machines running, and ultimately make their business better. So our very first tool for taming all this randomness is something called the random variable. And trust me, this is the foundation for everything else we're going to do. I know. Random variable sounds super technical, right? But honestly, the idea is so simple. A random variable just takes the outcome of some event, what the source here calls an experiment, and it just slaps a number on it. That's it. Think about flipping a coin. The outcomes are, heads or tails. A random variable just says, okay, let's call heads a 1 and tails a 0. Boom. Suddenly we're not talking about words anymore, we're working with numbers. Now, there are two main flavors of these things. For what we're doing today, we're really going to focus on discrete random variables. These are things you can count, like the number of cars you sell. You can sell 0 or 1 or 2, but you can't sell like 1.57 cars. The other kind, continuous variables, are things you measure, like time or weight, that can be any value in a range. And this table here really shows you how useful this idea can be. Look at that first example. The so-called experiment is just contacting 5 customers. The random variable, which we're calling x, is just the number of them who actually buy something. So what are the possible values? Well, 0, 1, 2, 3, 4, or 5. Simple as that. We've just translated a real-world situation into a clean set of numbers we can actually work with. Okay, so we can turn outcomes into numbers. That's a huge first step. The next obvious question is, what's the chance of each of those numbers happening? And that brings us to our second big tool, the probability distribution. So let's head back to our car dealership, which the source calls DeCarlo Motors. They've looked at their past data, and they've figured out the probability for each number of cars they might sell on any given day. So, for example, there's a 0.18 or an 18% chance they sell 0 cars. There's a 39% chance they sell 1 car, and you get the idea. And this just shows you the power of a good visual. That table is fine, it has the numbers, but when we graph it like this, the story just pops right out at you. You can see in a split second that the tallest bar is at 1. So, selling exactly 1 car is the single most likely thing to happen on any given day. Now, for any of this to work, it has to follow 2 really simple, common sense rules. First, as you can see, probabilities can't be negative. Duh, right? And second, if you add up the probabilities of every single possible thing that could happen, they have to add up to 100%, or, exactly 1. Makes sense, because something has to happen. Okay, so now we have our map of all the possibilities. But if you had to put your money on a single number that represents the average over the long haul, what would it be? For that, we need something called the expected value. And I just love this definition from the source. It's not just a plain old average, it's a weighted average. And what that means is that the outcomes that are more likely to happen get a bigger say. They get more weight in the final calculation. It's just a smarter, more realistic way to find the average. And here's the formula for it. Now, don't let all the symbols scare you off. It looks way more complicated than it is. All that sigma f of x thing means is you take each outcome, the x, multiply it by its own probability, the f of x, and then you just add all those little answers together. Seriously, that's the whole thing. Let's actually see it in action with our car dealership data. Take a look at this table. We've got our outcomes, x, and their probabilities, f of x. We just make a new column where we multiply them together. 0 times 0.18 is 0. 1 times 0.39 is 0.39. 2 times 0.24 is 0.48, and so on down the line. Then the last step is just to add up that final column. And when we do that, we get 1.50. That is our expected value. Now you're probably thinking, wait a minute, you can't sell 1.5 cars, and you're absolutely right. The expected value isn't a prediction for any single day. Think of it as the long-run average. It means that over hundreds or thousands of days, the average number of cars sold each day is going to get super, super close to 1.5. So now that we've got the basics down, let's look at a really cool shortcut. It's for a super common type of problem, and it's called the binomial distribution. A situation fits this binomial model if it checks these 4 specific boxes. You've got to have a fixed number of tries or trials. Each try can only have 2 outcomes, which we usually just call success or failure. The chance of a success has to be the same every single time. And finally, the trials can't influence each other. A perfect example, flipping a coin 10 times. Let's use a new example from the source to make this clear. A clothing store. Let's say we know that any customer who walks in has a 30% chance of buying something. So if we look at the next 3 customers, what are the odds that exactly one of them makes a purchase? This is a perfect setup for a binomial problem. We've got 3 trials, 2 outcomes, buy or don't buy, and a constant probability. This tree diagram is just a great way to visualize what's going on. It shows every single possible reality. The first customer could buy, that's S for success, or not buy, that's F for failure. Then the same for the second customer and the third. If you follow the branches, you can see all 8 possible combinations, from SSS, where all 3 buy, all the way down to FFF, where nobody buys anything. So let's just zoom out for a second and see what we've done. In just a few minutes, we've built up this amazing toolkit for dealing with uncertainty. We started with random variables to turn outcomes into numbers. Then we used probability distributions to map out the chances of each number. We figured out how to find the long-term average with the expected value, and we even found a handy shortcut for those success/failure problems with the binomial distribution. And really, this is the most important thing to remember. We are not building a crystal ball. Probability is not about knowing the future with perfect certainty. It's about understanding the shape and the rules of uncertainty, so you can make smarter, more logical decisions when you're facing it. So I'll leave you with this to think about. Think about your own job, or your hobbies, or just your daily routine. Now that you have these tools in your back pocket, what's one random part of your world that you could start to measure and map and maybe, just maybe, understand a little bit better?